Hello, today's physical chemistry lecture is on phase diagrams and phase transitions. I'm Dr. Andrew Tehemi. I lecture physical chemistry in the Department of Chemistry, Benue State University, Makurdi, Nigeria. If you need to contact me, you can do so using my email addresses, or you can leave your questions or comments in the comment section of the video on YouTube, and I'll do my best to respond. Today's lecture builds on the pre-lecture assignment on phase diagrams and phase transitions, in which I ask you to list the states of matter you know, to define a phase diagram and a phase transition, and then to use a hypothetic phase diagram and indicate melting, boiling, and sublimation. So, in this lecture, we begin with states of matter. Under that, we look at phase diagrams, and under phase diagrams, we define phase boundary, critical point, boiling point, melting point, triple point. And then we examine the phase diagram of water and CO2. We'll move on to phase transitions. We'll look at examples of phase transitions, and then we end it up with chemical potential. So after the lecture, I expect you to be able to define a phase diagram, phase transition, phase boundary, critical, boiling, melting, and triple points, as well as chemical potential. Sketch a typical phase diagram and explain it. Draw and explain the phase diagram of water and CO2. State the difference between a phase diagram and a phase transition. Give examples of phase transition. And finally, show that the chemical potential of phases in equilibrium is equal. Now, matter is encountered as solid, as in the case of stones, liquid, as in the case of water, and gas, as in the case of cooking gas. Of course, there are other states of matter, like the plasma state and the Bose-Einstein condensate. But these are not the focal point of today's lecture. So there are three basic states of matter: solid, liquid, and gas. And depending on the temperature and pressure conditions, a substance can exist as solid, liquid, and/or gas. That is to say that depending on the temperature and pressure, a substance can change from one state of matter to another without a change in its composition. For example, here is liquid water in the form of rain, and here is solid water in the form of snow, and here is gaseous water in the form of steam from water boiling in a kettle or a pot. So the solid, liquid, and gaseous state form the separate phases of the substance in question. So a phase is a state of matter that is uniform with respect to its chemical composition and nature of aggregation, both at the microscopic and macroscopic levels. Let's move on to phase diagrams. A phase diagram shows the regions of pressure and temperature at which the various phases of a substance are stable. So here is a hypothetic phase diagram: pressure against temperature. And at low temperatures and higher pressures, the substance exists as solid. As temperature increases, the liquid phase is more stable. Further increment in temperature leads to the gaseous phase being more stable. Whereas below this line, the gaseous phase is also more stable than the rest of the phases. This blue line is known as phase boundary. Of course, up there is no phase boundary. We'll come back to that in a moment. And the temperature at which there is no phase boundary is known as the critical temperature. Here is called the triple point, and the temperature at which that happens is denoted T sub 3. So let's define critical and boiling points. Let's assume that a liquid is heated in an open container. The vapor pressure will increase, and when it is equal to the external pressure, the liquid will vaporize. Now, the boiling point refers to the temperature at which the vapor pressure of the liquid is equal to the ambient or external pressure. If the pressure is 1 atm, we talk about normal boiling point or temperature. If it is rather 1 bar, we talk about standard boiling point or temperature. 1 bar is very similar to 1 atm. In fact, 1 bar is equal to 0.987 atm. For this reason, normal and standard boiling points are very similar. For example, the normal boiling point of water is 100 degrees centigrade, and its standard boiling point is 99.6 degrees centigrade. Let's consider heating the same liquid, but now in a closed container. When this happens, the vapor pressure will increase. The density of the vapor will also increase, while that of the liquid will decrease slightly. As the liquid continues to be heated, a time will reach when the vapor pressure will increase. The density of the vapor will also increase to a level where it's now equal to the density of the remaining liquid in the container. When this happens, the surface separating the vapor phase from the remaining liquid will vanish, leading to something like this. The temperature at which the surface vanishes is known as the critical temperature, and the corresponding pressure is known as the critical pressure. For example, the critical point of water is 378 degrees centigrade, and its corresponding critical pressure is 218 atm. Let's look at melting and triple points. Under a given pressure and temperature, a solid can coexist with its liquid phase in equilibrium. And when this happens, it is known as melting, and the temperature at which this happens is known as melting temperature or melting point. For many substances, the melting temperature is the same as the freezing temperature. When the pressure at which melting happens is 1 atm, we talk about normal melting temperature. If it is rather 1 bar, we talk about standard melting point or temperature. The triple point is the point at which the three phases coexist in equilibrium. For example, the triple point of water is 273.16 Kelvin, and it happens at a pressure of 1.0 6.11 millibar. The triple point also marks the lowest pressure and perhaps temperature at which a liquid phase of a pure substance can exist. So let's look at the phase diagram of water. The phase diagram of water shows the temperature and pressure at which ice, liquid, and vapor exist. So here is an abridged version of the phase diagram of water. At this pressure and temperature, the solid phase is more stable. As temperature increases, the liquid phase becomes more stable. Further increase in temperature leads to the vapor phase being more stable. The triple point is here, 273.16 Kelvin, and it happens at a pressure of 0.006 atm. And the liquid vapor line shows that boiling temperature increases as pressure increases. That's liquid vapor line, this one. The solid vapor line, which is this one, shows that sublimation temperature increases as pressure increases as well. The solid liquid line shows that melting temperature decreases with increasing pressure. And this is one differentiating feature of the phase diagram of water and the phase diagram of other substances. This line has a negative gradient because increase in pressure leads to the solid phase becoming unstable. And this is because the solid phase is less dense than the liquid phase. So as pressure increases, the liquid phase, which is more dense, is favored over the solid phase, which is less dense. So here is a more elaborate phase diagram of water. What we saw in the previous slide is indicated by this dividing region below. At high pressure, the bonding between the water molecules are modified, and that leads to more solid phases being formed. We've got ice 2, ice 3, ice 5, and then ice 6. And of course, as temperature increases, the liquid phase becomes more stable, even though there is high pressure. Yeah, so here is the phase diagram of CO2. This shows that at this pressure and temperature, the solid phase is more stable. Increasing pressure leads to the liquid phase being more stable. Further increment in temperature leads to the gaseous phase being more stable. The critical point lies somewhere there, 304.2 Kelvin. The corresponding pressure is 72.8 bar. The triple point lies there. It happens at 216.8 Kelvin and at a pressure of 5.11 bar. The solid liquid line, which we have to distinguish it from that of water, shows that melting temperature of CO2 increases as pressure increases, as opposed to that of water, which shows that melting temperature rather decreases as pressure increases. This is because for CO2, the liquid phase is more dense than the solid phase. So increasing pressure leads to the liquid phase, the solid phase rather, being favored over the liquid phase. Now, you will notice that the triple point is above 1 atm. Now, the triple point lies above 1 atm, meaning that CO2 cannot exist as a solid at normal atmospheric pressure, regardless of the temperature. And even if the solid is left open, it will sublime to the gaseous phase. You may have watched a candle burn. When this happens, the solid wax is converted to liquid, which flows down on the body of the candle and cools down into the solid again. This is typical of what happens when we talk about phase transitions. On the phase diagram, phase transition is the transformation that happens when a phase boundary is crossed, that is, crossing between the solid phase to the liquid phase, or vice versa, from the liquid phase to the vapor phase, from the solid phase to the vapor phase. Phase transition happens spontaneously and it occurs at a characteristic temperature and pressure. So here are a few examples of phase transitions: melting, moving from solid to liquid, and freezing, moving from liquid to solid, boiling, moving from liquid to gas, and condensation, moving from vapor to liquid or gas to liquid, sublimation, moving from solid to gas or vapor, or and deposition, moving from vapor or gaseous to solid. So let's look closely at what happens during phase transition. Let's look at the case of a transition from liquid to solid. We magnify the tiny little red dot there to something like this, a plot of temperature against time. As the liquid is cooled down, it gets to the freezing temperature and it freezes. And during freezing, the temperature remains constant until all the liquid would have changed from liquid to solid. And as cooling continues, the temperature falls again. And the transition actually happens at this point where the temperature is constant. And this is happening at a constant pressure. I should have mentioned that. Now, what is basically happening in this region? To help us understand this, let's look at a quantity known as chemical potential. The chemical potential is the measure of the capacity of a substance to initiate either a physical or a chemical change. Mathematically, chemical potential is equal to Gibbs free energy divided by the amount of the substance. And this is denoted by G bar and is called molar Gibbs free energy. At equilibrium, change in Gibbs free energy is going to be equal to 0. So let's say the liquid phase has a chemical potential of mu sub L, while the solid phase has a chemical potential of mu sub S. Let a small amount of the liquid phase changes to the solid phase. When this happens, the Gibbs free energy will change, and the change in Gibbs free energy will be equal to the decrease in the Gibbs free energy of the liquid phase plus the increase in the Gibbs free energy of the solid phase, and both will be equal to 0 because the two phases are in equilibrium. We rearrange equation 3 to obtain equation 4. The n cancels on both sides, and that gives us equation 5. Equation 5 is very important in phase diagram, and it shows that the chemical potential of phases in equilibrium is equal. Chemical potential decreases as temperature increases. So here is a plot of chemical potential against temperature. When the chemical potential is high, the solid phase is more stable. Increasing temperature decreases the chemical potential, leading to the liquid phase being more stable. Further increment in temperature leads to the chemical potential decreasing, leading to the gaseous state being more stable. In summary, the phase with the lowest chemical potential becomes the more stable phase. To summarize, we have defined phase diagram, phase transition, phase boundary, critical, boiling, melting, and triple points, as well as chemical potential. We've sketched a typical phase diagram and interpreted it. We've drawn and explained the phase diagram of water and CO2. We've stated the difference between a phase diagram and a phase transition. We've given examples of phase transition. We've shown that the chemical potential of phases in equilibrium is equal. So it's time for you to take the quiz. Define the following: the phase diagram, phase transition, phase boundary, critical, boiling, melting, and triple points, as well as chemical potential. What are the typical features of a phase diagram? State the difference between a phase diagram and a phase transition. Give 3 examples of phase transition. Show that the chemical potential of phases in equilibrium is equal. Thank you for watching. I invite you to like, comment, and share this video, and subscribe to my channel so that you'll be notified when new videos are uploaded. If you need to contact me, you can do so using my email addresses, or you can leave comments in the comment section of the video on YouTube, and I'll do my best to respond. You can download the PDF version of this lecture in the video description on YouTube. Bye now.